All right, welcome everyone to another Polymath Salon. This is the second one today because we're getting some cool stuff happening. Today we're joined by Paul Hahn, who's going to be talking on the evolution of electronic skin, but just in general, you could say augmentation of human skin in a sense, right? And we're also joined by some returning guests and some new ones. Morgan, you want to give a quick intro?
Yeah, hi. My name is Morgan. I do psychiatric neuroimaging, and we also run a community biolab here in San Francisco.
Oh, I'm just a generalist researcher poking in to see what's going on.
I'm a PhD physics student at FAU.
My name is Dugan. I'm a mathematician, geometer, and artist. I work at the Wolfram Institute as a research coordinator.
Hey, Scott Field. I practice real estate sales for a living here in South Florida. Studied economics and business, did business consulting during the dot-com boom, involved with machine perception and cognitive robotics lab, and just a very curious person.
We love that curiosity. James.
Hey, James Mavo, materials engineer, and wanted to pop in and listen to this interesting talk. So thanks for having me.
Awesome. And finally, Jess.
Hey, data science graduate, background in cognitive science, made cognition futures group at Orthogonal Lab, where I sometimes talk with Morgan there too. And generally doing a lot in startup innovation, leadership, futures, and spaces. Second, 2 for 2 today. So I'm glad to keep it going strong here. Thanks for putting together, Addy.
Of course, yeah, really fun to have two of these awesome conversations today. Real quick, before we do start, I hope everyone got a chance to check out Dugan's presentation at UT Austin on higher dimensional geometry and higher dimensional spaces. He presented right before the lead speaker of the UT Salon with Scott Aronson on computational complexity. The video is getting some decent engagement. Y'all should check that out if you haven't already on the Ekkolapto channel. But yeah, let's get started, Paul. Quick intro and then take it away.
Hey, thanks so much. I'm really excited to be here, and everyone looks so interesting. My name is Paul Hahn. I'm the founder of Aurem Labs. We're a bioelectronics company. We basically make biofeedback devices that operate in a mesh network. I'm an electrical engineer of 5 years. I went to Yale, and I set my life on fire when I was 7. I've been building stuff since I was a kid, and this is what I love to do. I'm really excited to share with you about basically human electronic skin for human augmentation. The focus of my talk will basically be a brief summary of the fact that this is an active field. There seems to be a turning point right now, that it has practical use cases. And finally, the bulk of the talk will focus on the material science and engineering considerations in actually creating this kind of stuff. All right, so let me just go through some papers, like screenshots of papers. Everyone loves these things. 25 years, evolution of electronic skin. That name at the bottom, Zedong Bao, just remember that one. A really famous material engineer runs a group at Stanford. So yeah, the basic idea of like making electronic skin. The reason why you want to make electronic skin is that skin is like actually extremely complicated. It has a lot of sensing capabilities that would be advantageous in AI, robotics, medicine, augmentation. And also is like actually very sophisticated in the way that it senses things. For example, there's actually no sensor like on the market that is as sensitive to touch as like our human skin is. The density of the pressure sensitivity of human skin is about 1 millimeter squared. So you can detect the difference between about 1 millimeter differences in pulses and like basically things being pushed against your skin. Additionally, it's not just pressure. Like you can tell the difference between like basically like rubbing 2 pieces of skin together. That's kind of like shear forces. You can tell between like acceleration and kind of the and there's a sort of kind of like the speed of like the pressure. And also that doesn't really seem to have enough. That doesn't really seem to depend on like the temperature or other conditions, which is another problem when you design these things using hardware. There's other pages. Decoupled sensory signal monitoring and human interface systems, more electronic skin. The Bao group, which is made by like basically there's literally a group at Stanford called like basically electronic skin group by Professor Bao, and they've been doing this stuff for actually like a number of years. One thing you'll find in this like presentation is that a lot of the technologies used for electronic skin have kind of been like backported from like other fields. simply because like, you know, right now there aren't really that many, there aren't huge commercial desires of human skin, right? And that's actually really the case for a lot of technologies, right? So for example, titanium carbide MXing is actually a really important material for the development of electronic skin. That was actually developed for the battery industry. I mean, that's like obviously tens of billions of dollars industry, hundreds of billions of dollars industry. That's kind of the case when you look at the history of technology. There are some like commercial needs for like certain sectors, for example, like Teflon in the Manhattan Project or NASA. And then like the use cases of these like kind of developments for like major commercial technologies are then backported into more fundamental research. Then that allows that fundamental research to become like a huge commercial need. And that's kind of like a cycle of technology development, at least kind of how I see it. All right, so electronic skin versus electronic tattoos. So like a tattoo is like very thin, right? It's like kind of like sub 100 micron, while skin can be like a millimeter, 2 millimeters thick. The difference between that is that like electronic skin on the body, you can kind of notice it. Electronic tattoos, you don't really notice it. But then obviously, like the more technology you can fit on a thicker object, right? So right now, like electronic tattoos are kind of like, they don't really have power sources. They can't actually measure that much. They only last for like a couple hours or maybe a day. Electronic skin is a lot more sophisticated. You can do electronic noses through kind of like chemical sensing. Actually, what's the closest analog to like an electronic nose and electronic tongue today is more kind of like sweat sensors. So like there's a lot of interest in sweat sensing for kind of like athletics, psychological, and kind of like health-based monitoring. For example, like in your sweat, there are like hormones like glucose and lactate and cortisol for like stress. So if you have a sort of like microfluidics sensor, you can use that to kind of like detect the different hormones and compounds in your sweat, and you can use that to kind of develop your devices. Multimodal AI embodiment. This is like not the area that I deal in, but that is also a great commercial need for electronic skin. For example, like I always think of like real life as like much more higher definition than like anything that I made. Like if you look at like if you just like go in nature and like look at trees or like look at leaves and like I don't know, go on the golf course or something, you notice that like there's so much more detail in that sort of environment than like anything found in like the city. Simply because there's just not enough resolution. There's not enough like design intent in man-made objects. So I'm personally of the belief that like AGI will come only with like an embodiment of AI. And so like generally, yeah, like you want electronic skin as if to feel, sense, and touch. I mean, I'm a tinkerer. I'm like an engineer. I love designing things. Like in this office right here, I have a lot of equipment. There's just a bunch of stuff you can't read about in the textbooks, and you can't predict. You kind of just have to like touch it with your hands and like smell it or just like listen. Actually, it's funny. Like right here, I have like a big UV laser. There's supposed to be like a sort of like focusing rack system that uses like basically like a vision system to do it, because the focal depth of like the UV laser is actually very thin. I don't have that right now, so honestly, what I do is like I just tune the knob, and like when the sizzling is like loudest, I know it's like in focus. And that would actually be extremely difficult for like a machine to replicate. That's just an example of like I hope that example kind of gives you the idea that like, okay, if we had sort of like electronic senses similar to comparable to human senses, that may allow for greater and richer understanding of the physical world. And it's not just like science fiction or just like you know, kind of like a cool aesthetic. It fundamentally allows for a much deeper understanding of the physical world. Another way to put it is that like they didn't make a robotic horse. They made like a car. I would counter that like in that specific example, like horses were really only meant for like one very specific task, which is like moving things from A to B. But the whole world is designed for people. And even now we can't make an electronic horse or a mechanical horse. So I want to advance the opinion that like a humanoid robot that has sensory abilities similar to a human would actually provide fundamental benefits over a special purpose machine. PDMS, platinum silicone. So like if you read the literature, you'll hear this word a lot, like PDMS. It's honestly, this is just like mold making like silicone for like Hollywood. Okay, so like if you read the literature, they'll talk about EcoFlex a lot. Do you know what EcoFlex?
Is this similar to like the smooth on silicone stuff?
Yeah, you're just right. Yeah. It's literally just that. That's what they're Yeah, it's literally, I mean, all these researchers for their like really fancy advanced electronic, they're literally just buying from this company. This is what they talk about literature. This is EcoFlex 31. Shore rating is basically like a measure of sort of the flexibility or hardness of the material. Shore A31 is roughly equivalent to human skin. Shore 10 is about equivalent to Shore 0010. Sorry, is about equivalent to like kind of like muscle, kind of like the squishy stuff inside the body.
Right.
They're all buying it from this company. It makes a lot of sense too, because like obviously since this company has to make stuff for like prosthetics, it's like biocompatible, it's non-toxic. One thing you'll find is that in electrical engineering, when you design circuits, it doesn't really matter if the stuff causes cancer. Like lead solder is actually really great. Like it's not like they put lead in things because like they were evil. Like lead actually is an extremely useful and versatile material. Lead paint is fantastic. So actually one of the big challenges with bioelectronics, and I think one of the reasons why observers might say that, hey, like this field seems to be moving very slowly. There isn't a lot of, it doesn't seem nearly as advanced as sort of like conventional electronics. A lot of problem is that like you can't kill people and it can't kill cells. For example, like let's say you're trying to make a microelectrode array for growing neurons, which is what my friend is doing right now. This is really annoying because like a really easy material to use for electrodes, for like conductive electrodes is actually like silver. Silver is fantastic. Silver is fantastic because it's like the most conductive material. It's very easy to work with. You can plate it, you can spray it, you can like use ultrasonic deposition, you can like sputter it. But silver is also antimicrobial. So like, you can't grow neurons on silver. The neurons are very fussy about where they grow. So actually what you use is something called titanium nitride, which is what's used in like pacemaker electrodes. And that's a little more fussy to work with. It's also not nearly as conductive. It's actually a conductive ceramic. Another thing I want to go is UV hydrogel. So like, okay, I want to show you a picture of basically like, you've seen these in like the medical office, like 3M. So like you've seen this in like doctor shows and whatever, like these like electrodes that go on like the EEG machines, right? Yeah. So like, let's talk about like what's inside this thing. And I have some in my office right now, but I'll just kind of like open this picture and I guess I'll just like explain to you what's in here. So the reason why you have this kind of like piece of plastic over this other piece of paper, it's like actually sealing like moisture. There's kind of like this wet goopy stuff on top of this kind of like darker black electrode. This darker black electrode is silver chloride. Silver chloride is over something called hydrogel, and then that's kind of sealed. And this is actually what's called a hypercolloid like adhesive, and that's what's stuck to the body. If you kind of make a table of like flexible, conductive, and adhesive, and like try to find materials and also biocompatible, and you find kind of like materials that meet all those properties, it's extremely difficult. And so that's one of the challenges of bioelectronics. If you look at like a stack of like a PCB, so this is like a regular PCB that you'd find like when you make a circuit board. This is what I did like every day, right, as an engineer. What this is like basically these are cores of FR4, which is a form of fiberglass, like similar to the fiberglass insulation in the home. And this is like copper, and there's sort of this like nasty, like caustic, carcinogenic like adhesive that like bonds it all together. Basically, they like kind of like put glue over all these different layers, and then they put through big rollers. So like basically, this is how circuits are made, right? It kind of makes sense. You have wires, you have components, you link them all together. And I just told you all the reasons why you don't want this to like go in your body, because like it's toxic. So really, and also it's stiff. It's like it breaks, it's fragile, it's brittle. So like really what's ideal for making electronics work is exactly the opposite of what like our body is like. The fundamental, I think, challenge of bioelectronics is making stuff that like works for electronics, but is friendly to the body. And that's not trivial at all. And so I think it's actually mainly a material science problem of the field. When I was a kid, I read this book called like Napoleon's Buttons. So when Napoleon invaded Russia, his like soldiers' uniforms were made out of tin. And it was like a tin antimony alloy or something like that. The problem is that it was a Russian winter, and so like the tin was so cold that it became brittle, and his soldiers' uniforms like basically fell apart. And that's one of the reasons why Napoleon lost, because the soldiers' uniforms can handle things. This book is about material science, and like, yeah, it was one of my favorite books. Going back onto that, like, this is kind of like an attempt of making a sort of like circuit work for the body. And basically, there's a lot that goes into that. For example, I could talk about like how you like model the body skin as like from electrical perspective, like why you need this sort of like poopy stuff in between like the metal and like the skin, why the metal has to be specifically silver chloride, why you need like a separate piece of tape instead of just having one sticky part in there. So yeah, I've kind of like given a broad general case of like the sort of things I can talk about. And yeah, I just want to open myself to like where you guys want the conversation going.
Awesome. No, this is really cool. I mean, I guess the one of the things that I think about, right? Because this is basically kind of a look at kinds of augmentation you can do, right? In a sort of very futuristic sense. What do you see as the potential for this kind of stuff? Like, if you had to sort of be very, maybe more on the side of a sci-fi potential, like what is the coolest thing this could look like? Because I'm very interested in where modern computing frameworks and technology intersect with biology. Right, so the idea of electronic skin is very interesting, and skin that lets you kind of interact with the computers around us directly, almost like a force touch in a sense,
Yeah. So okay, let's say you got your arm cut off. Anyway, so you get a prosthetic arm. Right now, your prosthetic arm, it's just like a piece of plastic metal attached to you, right? And you've seen those videos where they have like the EMG sensors and like move their arm. But the thing is, they can't feel their arm still, right? Like they can't feel their arm at all. I think people focus on like, okay, we need to make like a link between like the nerves in like your amputee arm and like the prosthetic robot. But like I think also another side of the equation is like, how do you actually get the sensors in the prosthetic arm to like give you the sensation of touch back to you? So like. Right. On like a sort of like a near-term scale, you could imagine a prosthetic arm that like helps like people like regain a sense of having an arm. Let's take it a step further. What eventually the electronic skin will be like better than like your regular skin, right? So like maybe electronic skin like works at lower temperatures or higher temperatures, or like you have much greater sensation of touch. You can like kind of like download sensations of touch for like, I don't know if you want to do stuff like that.
Expand more on the download sensations of touch. Expand on that, because that sounds pretty interesting.
Yeah, so like I guess like another application of this is like VR. So like imagine like a sort of electronic skin glove you put over your body, over your arm or your hands, and basically the end goal is giving you VR tactile sensation without having to like get invasively Neuralinked on. Let me explain how. So like a lot of the research deals with sort of like these fact that like skin has a sensation of touch. When you touch something, it's your skin that feels that you've been touched. So you could have an electronic skin that also has this tactile sensation. Conversely, you can have an electronic skin that actually induces a sensation of being touched as well. There are two main ways of doing this. One is like quite obvious. One is simply having haptic feedback, like a phone, right? You have haptic feedback. You have like a piezoelectric buzzer built into the skin, and so you'd wear the skin on top of your own skin, and then like it would buzz in specific locations. And so you could imagine a VR situation where like your VR character like bumps into a wall, and feels like I don't know, like a furry stuffed animal, and like electronic skin in the real world gives you that sensation of touch as well. Okay, I got a question on like using electronic skin where it creates electric fields to guide the growth of flesh. Yeah, there are basically like e-bandages. So like, okay, actually,
yeah, I know about these. Yeah, I've seen these. Yeah, this is interesting.
So like, my company actually mainly deals with sort of like biofeedback, and like actually on the electrical side. And so like, I don't directly deal with, I personally don't think that the electronic bandages will come as quickly as some of the other stuff due to regulatory needs. There are some electronic bandages on the market for like military applications. The general idea is that like wounds, all these ideas really are just like, okay, if we apply electricity to the body, what happens? Okay, let's apply electricity to the body in a more sophisticated way. All right, let's like apply a specific electrical signal to the body and see what happens. So like, yeah, you can like get an electronic bandage that basically is electronic skin. It has these electrodes. It's called TENS. And like you stimulate sort of a wound and it makes it grow faster. One problem with this is, first of all, the FDA is like really very touchy about like injecting electricity into the body. Yeah, it would be like a class 2, class 3 medical device. The second thing is that like probably there's like a specific like waveform that like causes a better effect than others, right? And it's very difficult to tell. For example, like in TMS or transcranial magnetic stimulation, you know, they actually target like a fairly rough area of the body, of the brain. And also transcranial magnetic stimulation is basically they aim a big like kind of like magnetic pulse right at your head, and they use it to treat depression, anxiety, ADHD. And I guess one of my suspicions as an engineer, and I wonder how you guys feel about this too, is that like, all right, like all these sort of like electrical stimulation things, like they all seem to have like a very broad category of like uses. Okay, it treats ADHD, it treats autism, it treats depression, it treats anxiety. It makes your wounds heal faster. It like makes your muscles relax. I mean, it seems to me that probably the direction is going, and that like if you get enough people to like wear electronic skin or wear electronic patches, and you can like collect enough bioinformatic data, that there's probably like a very specific signal that like has a much more powerful but specific effect. That's just kind of my intuition to do that. All these things seem to have very broad descriptions of their use cases. They're all good too. You never tell you like, oh, TMS will make you afraid of like bananas, you know, and they never tell you that.
Well, I do also know that, I mean, I guess there's the things that are in the scientific literature, and then there's the ones that are sort of anecdotes off of Reddit and X and all that kind of stuff. But people have most certainly had negative effects off of these kinds of, let's say, electrical therapies, you could say. I mean, there's many stories of things going just insanely well for people, but then also sort of the opposite. And, you know, this is actually something I was very, really fascinated with for a long time in terms of things for cognitive enhancement and all that type of stuff, right?
Well, I was just going to say, you're now starting to talk about psychiatric applications of electrical stimulation. I can certainly speak to some of those. One of the reasons that you see these broad categories across TMS and TES, as we call it, for TDCS, TACS, TRS, is that these don't have a lot of evidence, and these are getting used in a way that is self-pay, and it's hard to distinguish from placebo. SAINT, which is a new Stanford protocol for TMS, is showing a very high rate of success in depression, but a lot of people are waiting to see larger studies done outside of that particular group to see whether, like a lot of times what we get are very good reports from a particular lab that pioneers something, and then as the protocol trickles out to other groups, you'll see the effects subside or not as clear. We'll see. But I just wanted to distinguish that from electrical stimulation for bone healing, right? Which is a very easily, is very well documented.
Sure.
Effect.
Yes.
And the wound healing and electrical stimulation for it, both in bone and in more general wounds, is really remarkable. And I'm, I don't think these are connected. Is the thing. We don't look at electrical stimulation as kind of like a neuroplasticity. Well, I shouldn't say that. I mean, it's not neuroregenerative, right? Even if, like, again, like, I don't want to get too down in the weeds of TACS or TES papers in terms of, what it is changing potentially. One of the things that we know, and Jess knows, I brought this up before on our meetings, stress is the interplay of someone's job. So say a caregiver in a nursing home, right? Given a small wound in terms of, a small incision on the hand, and then versus people in other professions, and then looking at wound healing time, right? So it's like an interesting, one respect, it's interesting from just how stress and perhaps sleep deprivation and other things can cause wound healing to be slower, coupled with what we know from electrical stimulation, that wound healing can be faster. I think is really interesting, and I would love to see more research work on it, or a better understanding of the mechanisms behind that. If you've got any papers or links, yeah.
Morgan, I'm sorry, I might disappoint. I suppose I'll take it. I guess I'll offer my sort of electrical engineering perspective on it, which is all right. It seems like all these things kind of measure electricity from the body and then apply electricity to the body. So if we can simply design systems that measure electricity to the body in better ways and apply electricity to the body in more sophisticated ways, then good stuff will happen. That seems to be my general heuristic on the matter. Yeah.
So something else I've been thinking about. So this is sort of more on if we had these kinds of skin augmentation devices for children and the way that they learn their sense of touch. So I'm very curious from a neurological developmental background, right? For anybody in the audience, right? If you give this to a very young child who's just sort of learning their senses and how to interact with things, how will they potentially understand their sense of space differently as well? Because I know that for a lot of people, the sort of tactile sensation of texture, of air and wind on your hand or your arm, or all these different things, especially when they want to do something like sports and different kinds of spatial skills. I'm wondering how this I could see this as potentially enhancing that. Just a question.
Oh, so you mean giving people kind of an extra sensory capability?
Yeah, with an electronic skin kind of thing. So, and I think this could especially be useful, potentially earlier on in life. I'm sure an IRB may not approve of doing a study on that, but just for sake of experiment, right? Because I'm very interested in human augmentation for the sake of cognitive and biological enhancement, right? So things on longevity, being smarter, better memory, yada yada, all that kind of stuff. And I would think a lot about how could I use something like this to gain some kind of spatial spidey sense? Because there's some people that just off of a very subtle physical touch of things, they get an idea of something because they're just more sensitive to touch. It's like if you've heard of people with really good eyesight, hearing, the super smellers, people with a very good sense of smell, right? So that's who's a super toucher, right?
Okay, so my general heuristic for this, in terms of running a company, is that it's very hard for people to buy things they haven't experienced or have no idea of, and also a lot of these sorts of extra sensory capabilities, intuitively, they seem to require a lot of big data or a lot of bioinformatic data. So you kind of have to get people to buy something that has these sorts of sensors and then unlock that ability later. For example, with an iPhone, the iPhone had to make calls first before it could I don't know, run your life. It has
crawl
to be
before you run, basically.
Yeah. But in a very, I'll give an example of this. For example, the silent speech stuff, everyone loves that. Everyone loves the silent speech, talking to AI, not talking, whispering. The problem is that EMG is a data problem. So you gotta if you were to sell an EMG microphone, you basically tell people, hey, buy this microphone. You gotta wear this on your neck. You gotta wear this on your neck, and 100,000 other people gotta wear this on your neck. We all gotta wear this on our necks for a month or 2 months or maybe 6 months. And then after that, it's gonna work, and you're gonna love it. So you can't sell the EMG microphone first. You gotta build something people will buy, and then make it into an EMG microphone. That's kind of the thesis of Aurem Labs. To get on your point of like extrasensory touch. So like, yeah, it's interesting because like nature in some ways is like much more intensely sophisticated than man-made objects. At the same time, man-made objects have some clear advantages in some areas, depending on like what the use case is. I'll give an example of like, like with like the lab-grown meat and like kind of like engineered food that is coming of age. Right now it doesn't taste as good as real food, but I do think that I think there will come a day pretty soon where it will taste better than real food. Like, if you ever watched that movie like Soylent Green with like Charlton Heston, 1976, and in Soylent Green, the soylent is like not actually very good. It doesn't taste that great. And so there's a scene where like Charlton Heston like goes and eats like real food. It's like contraband, and he's like, wow. There could be a future where Soylent Green actually just tastes better than food, and that like I think that like nature sets a high bar, but I suppose the thesis of the company is that like nature can be surpassed. So in the question of like, okay, extrasensory touch, right now, mechanical or man-made touch sensors can very easily touch things not touching it. As in, like, for example, with your iPhone, like you can like wear gloves, or you can be like slightly above this of the touch sensor, and like it will still detect the touch. That's because generally those are passive touch sensors, and there's kind of a passive effect like outside, like a little farther away than like the surface, and that allows that to work. Unfortunately, that's also like a really annoying thing, because when you actually try to design like an electronic touch sensor, you find that there are tons of parasitics, like the temperature, the things around it. Like, for example, imagine if your sense of touch was messed up if like a soda can was next to it. Like imagine you had a passive touch sensor or a magnetic touch sensor as your skin, and if you went next to a soda can, the metal in the soda can like caused you to like have like weird hacky like sensations. It wouldn't work very well, right? So yeah, it's really constraints management. Oh, here's another thing. You can let people see through walls. Near infrared spatiotemporal color vision in humans enabled by basically what they do is you can see IR light. You can see infrared light if you wear these contact lenses. How does it work? All right. So if you think about a fluorescent light bulb or a cathode ray tube or like an OLED, think about a UV glowing object, right? What does a UV glowing object do? It's made out of some sort of substance that when you shine a UV light on it, it emits a visible light. What that means that it's an up-converting phosphor, in that you can shine light of a particular wavelength, and with some efficiency loss, it will convert those photons to a different wavelength. So basically, what they do is like they take contact lenses and they coat it with like UV glow-in-the-dark stuff, and then they put in your eyes. And so that means that when you shine UV light, you can see UV light. Okay, what are the problems with this? First of all,
I didn't read the study, but I did skim the HN comments like when it came out, and there was like a top 3. One of the top comments was like, "Oh yeah, not actually, just like you need amplification or something." I could be wrong, but I think if we actually skim it, there might be a little bit of a nuance where, oh yeah, it opens up the possibility of something, and it's.
You can have up-converting phosphors that like turn infrared light into visible light. The problem is that most of them are opaque, as in like you can make a contact lens out of them, but like you wouldn't be able to see because that's kind of useless, right? So the challenge is creating a phosphor that is both transparent to visible light and also does the up conversion of the UV of the infrared light, and that is actually the advancement in the paper. It's possible, based on what Eli mentioned,
Got it.
that like it's possible that the conversion efficiency of the phosphors is not high enough. They use basically like these kind of like gold nanoparticles. I'm not particularly familiar with those chemicals in particular, but I do know how they would I'll explain actually how they would actually make this sort of thing. For example, a CFL. Okay, how efficient is a CFL? Like a 10% efficiency. Okay, why is that? There's a couple of reasons. One is that, how does a CFL work? So there's a broad category of devices called gas discharge tubes. Gas discharge tubes are that if you put a low pressure gas in a low pressure gas and apply electricity to it, it will glow. It ionizes plasma. You can do this with different gases. The first common discovery was like hydrogen and like neon. So like neon signs, basically they put like low low pressure neon in a tube and apply electricity and it glows. But it's not very bright, right? So the point of a CFL is that we want to turn this light, which is not very bright, not very useful, into light that like pretty simply approximates a light bulb. So what they do is that they actually use mercury vapor. They take, okay, so if you look at a picture of this, all right, so this is a mercury tube rectifier. It's actually not really important what this does, but this purple glow is actually UV light. What they do is they take a little bit of mercury inside a tube and then they heat it up and then they apply a voltage and it glows. And this lets off a lot of UV radiation. It's basically how they made UV lamps before like UV like solid state diodes. All right, so you take this UV light and then you add the phosphor of the CFL. So basically this is a low mercury. If you didn't have this white stuff, it would actually glow a lot like this. The white stuff turns the blue UV light into visible light. And actually, the reason why CFLs used to be really bad, but have gotten better, is that like there's basically like the quality of the phosphor is a very complicated material science problem, and like there's something called like color rendering index. Basically means that like imagine like the sun. You can see all the colors in the sun. If you imagine a red light, you'd see everything in red. There's probably like some sort of like middle ground, right? Where like certain colors of light allow you to see more colors. Finally, sunlight, you can see all the colors that you can see. Is it kind of clear how I'm using the explanation of like neon tubes and CFLs to like explain the like X-ray vision, like contact lenses?
Yeah, I think we're this is sort of clicking. I mean, when I think of whatever it is that I'm trying to make or what other people are making, my first question is always, what is sort of the most immediate practical use cases, right? And then what are the ones that are a bit more kind of lofty and dreamy? A lot of, I think the sort of qualities of good engineering is also knowing how to get the product in the right market at the right time in the right format, complying with regulations, all those kinds of things. And I guess you have, experience with that you were writing about.
Oh, yeah. I mean, just to speak briefly about that, like one of the examples is sort of, if you have a device that can do multiple things with multiple degrees of, affecting privacy or affecting capabilities, and the market is really used to a certain way of interfacing with things, you kind of have to play where that is, but then you're making these strategic bets and challenges of, can the market shift in this way or not, and what can go in that direction, and where are you in the development? And you kind of have to stage, are you going to have the engineering team work on which part of that right now, and can you get a multiplier effect or not, or how do you stage that whole thing? So that's a big part of it that we can talk a lot about.
Yeah, I mean, my thing was, I definitely think sort of having different ways of having sensory experiences. Do you know Yo-Yo? Yeah, so Yo-Yo is working on this with a couple other people, with Lucy and Shresh, on basically send computing. So I'm wondering, I know you'd mentioned it a little bit earlier about olfaction, but I'm wondering how this stuff would also apply to sensing smells and being receptive to different kinds of smells and stuff like that.
Yeah, the nose is like really good. The nose is a really good sensor. It's fantastic. It's actually extremely precise, and like nothing's on the horizon that can really match it from my understanding. So like, for example, like what is the closest thing? Like the closest thing would be like a gas sensor. All right. So, and this is not nearly sophisticated.
About how broad would you say is the sensory capacity of the olfactory bulb? Like how many different types of smells can we smell?
There was like
Hundreds,
another
I think.
Ekkoleptic thing where there's like mentioning like the bass like receptors in the nose or something. Somebody mentioned a number, but now I don't feel comfortable even quoting it.
They said it was
probably Yo-Yos, right?
Yeah. Like somebody mentioned it. I think I heard the number 40, and then I also heard a number like 80, and like I can't remember exactly what that was all about. But
The challenge is we can't create
Right.
buckets like we do with taste. So with taste, we have like 5 senses, and we can say combinations of those different senses: sweet, salt, bitter, umami. I don't know what I'm missing.
Well, now you can also get into if you want to get into sort of the yo-yo and Lucy territory of things, is also sort of the quality of what olfaction, scent, taste actually is. And for me, I think, as much as I love thinking about all these kinds of things and being very kind of philosophical with it, I like to say, I like applied philosophy, which in many ways is almost good engineering, right? Good building something. I'm interested in, like, have you heard of like adaptable, like the sort of quote unquote self-healing materials?
Yeah.
So especially if this is going to be used as some kind of outer surface on something. So let's just say in an idealized state, someone does have, let's just say, an electronic skin, something that they're wearing, like a temporary tattoo, a glove, a sticker, whatever, right? I'd be very interested in the ways that could actually integrate with the skin, like physically, chemically integrate with the skin. So I think there are people that are studying how wearables can actually, if they're made from certain materials, can actually integrate with the body. I guess technically we already do that for things like pacemakers and all that. But I'd be very interested, one, how choosing the right set of materials could potentially integrate this, like, with the skin in a more kind of, I don't want to use the word natural, but in a way that it would look more natural, as if it's sort of naturally evolved, right? And then the second thing would be, if we're assuming there's some kind of integration and it's going to be there for a long time, how does it kind of adapt if it gets scratched, damaged, has some kind of damage somewhere? So there was something, I don't know how much research is going into this now, but there was something about, like, there was this field of, like, self-healing materials. I haven't followed it as much lately, but I'm curious about self-healing materials applied to this electronic skin thing that you're working on.
Yeah, so basically, like, the way you want to take this is, if you really want to go to, like, a nanofiber based system, like, you want to spin nanofibers if you really want it to match the properties of skin. Basically, so like, okay, so, like, what's the difference between, like, a piece of rubber and your skin? A piece of rubber is like a solid composite material. It's pretty dumb. It's simple. There's not a lot of information there. The skin is not only structurally sophisticated, it's also like it also has, so, like, there's many different materials in that skin, and not only there are structures that have properties based on not only the different materials that those structures are made of, but also the physical construction of those materials as well. So, for example, this is way more sophisticated than like any piece of, like, metal or glass that you like CNC or anything like that. Why? Because, like, they're different materials. They're like oil glands, muscle glands, sweat glands. They not only have a different shape inside this, like, supposedly continuous material, right? Our skin doesn't look like it's very complicated, but it's full of all this different stuff. So there's different materials in here, and the materials are in different shapes. And that's very difficult to do from a sort of, like, traditional manufacturing material. That's true. Yeah. That's kind of like a 2D, like, Eli asked, like, high-end phones have, like, 512 layers. Like, okay, so that would be but that's kind of like a 2D plane, right? Like, they kind of make things composite material, then make a 2D diagram, and then they kind of, like, glue it all together. But we're talking about, like, a 3-dimensional object that's being formed. And also in sort of like if you look at sort of like how circuit boards are made, like, it's really just one material per layer. But when you look at skin, it's got all these different things. It's completely 3-dimensional. So the way you make stuff that's self-healing, the way you make stuff that's, like, kind of, like, more akin to skin, you want to do stuff like nano. You want to basically 3D print nanofibers. You want to 3D print nanofibers, and that's, like, it's so you can create nanofiber fabrics where we're basically, okay. So the basic thing is that, like, at the nano level, like, the structure of the material actually changes the properties it has. For example, for example, one engineering problem that I have is that, like, you want to add, like, silver to like rubber to make the rubber conductive. If you just use like kind of like silver that you like kind of silver the fineness of like salt or something, you need a hell of a lot of silver inside this rubber, which causes it to not be rubber anymore. It like stops being flexible, it stops being transparent, etc. If you make the silver a really small nanoparticle, and also something called a nanowire, which is kind of what this looks like, you can get you can add much less silver to the rubber, and it still has the properties of a conductive material. So actually, yeah, I think in your point of like, how do you make the electronic skin more human-like? Not only structurally, which I just talked about, it also has to be more biocompatible. Like, for example, like
real quick, Paul, I did want to say it's not necessarily sorry to interrupt. It's not necessarily that I want it to be more human-like out of necessity. It's more about I'm really what I'm sort of chasing after is if it is being applied to humans, then sort of better integration with the skin, right? And then also what's more interesting to me is that just for the ability for it to adapt and heal, right? Which could be doesn't have to be a human, but just the principle of adaptation and self-healing materials and things like that.
I do know that there are materials where you can like cut it once and it'll heal once. I do know that you can get something that will,
I do want to interject to mention. So I've had the Honor Magic V3. So I've seen all kinds of random things that say they claim to be self-healing, and this is actually astounding. I've had this phone for 8 months now. It's not in the US. They're probably violating every patent so they can use as much cool stuff as possible. But I have scratched my screen with like fingernails and small objects multiple times and got 100% recovery. And it's quite astonishing on this device, whatever they're using for the specific layer on this phone. I've had 5 other folding phones. None of them have been this insanely like healing. So it's something to look into, whatever they're using on the Magic V3. Some kind of fluid layer. Yeah. Look it up. It's interesting stuff. They're going to have a new one out in the next couple of months. I imagine they're not going to regress in that part. So more stuff coming in. And I really hope to see this in the folding laptops coming out soon.
Oh,
because those are not glass usually. They're just plastic.
Oh, is this a hydrogel? Did they just use hydrogel?
I think, yeah. It might be. It's something like that, but it's very effective. I have scratched this screen like at least 10 plus times, and I cannot find any of the scratches anymore. So sorry for interrupting.
Oh, my fault. That was awesome. I didn't. Actually, yeah, hydrogel. Yeah, I guess it's self-healing.
Since this stuff has to be like biocompatible, would it be possible to avoid the necessity of precision 3D printing and instead just create like some sort of like synthetic organism which just like grows the electronic skin as it is? Okay, so you know how you can like grow some skin in like a petri dish, but like if you kind of remove it from like that environment with all the nutrients and stuff, it'll just like die. What if you like have this organic genetically modified like skin like thing, which when it's growing creates these like I guess like organic but not necessarily alive like biological like structures, such that when it is like eventually removed and the organic parts like the biological parts like die, there's actually a functional electronic skin like left over that can still be used.
But why wouldn't you just grow it before you sell it?
Well, I mean, the idea is that you're growing it instead of like 3D printing it, and that's the product.
Oh, I see. So like okay, so like like my mentor does like an artificial
I don't know how like that seems like it'd be like fairly difficult with like our current stuff, but like it seems like it should be at least hypothetically possible in the future.
Yeah, so like my mentor, like Professor Burge at UConn, he basically does this. He basically goes the other way where like he takes like basically biological stuff and tries to kind of like command it as you would like a natural like a man-made material. Where I suppose like the stuff that like I kind of work on is like taking man-made stuff and try commanding it to act in a more biological manner. Yeah. So actually, he published this like interesting article. Like in like 1995, he published this like interesting article called like you can't see it, but anyway, he published this interesting article called like protein computers. So basically, like programming proteins to like act in that sort of way that you describe, and also use it for computation. Yeah, that's one way of doing that. Another way.
Interesting.
Yeah, funny you mentioned this. We've actually done some salons in the past, in person and online, on unconventional computing, and within that forms of biocomputing, things like DNA and protein-based computing, which is very fascinating. But something that I kind of think about, right, is what types of problems are we trying to solve, right, where technology starts to look more like biology, right? So if you go for a skin that's some kind of electronic skin that is using, let's just say if we pace after certain characteristics, it trends and starts to look a little bit more towards biology, right? So I think if you want a really good, adaptable, high agency robot or something, it's going to start to look a little bit more like a human. Doesn't mean it's literally going to be made of flesh, but it'll have some kind of analog that functions similarly, where it's able to respond more quickly to different things on its skin, and it's analog of a skeletal structure, all those kinds of things. And for me, I guess since we're going in that territory a bit, is that what does this sort of look like when fully merged with biology, when you can't necessarily say this is biology or this is some kind of implant, this is just something entirely in its own category, right? So I think when on the topic of integration is, can you have, and this I think this goes beyond skin augmentation, but just in general human augmentation, right? Where the devices that we're using to augment our body are so integrated that they're basically indistinguishable from biology, right? They're just like a higher tech biology. Like there's this, for one of the biocomputing salons, I brought up the idea of like, what would a at least semi-biological Neuralink look like?
Yeah, I think like, all right, I guess, okay, so like the focus of the company is just making more conscious processes unconscious. That's really it. You take, yeah, that's it. That's my.
I like that. So all right, so then we'll focus on Aurem a bit, right? So what does your game plan look like with Aurem Labs for the rest of this year? Like, what are you kind of chasing after right now?
Yeah, so basically, what's interesting, and I'm this, you learn this, it's easiest to like hire people for like tasks that how to do really well, which is kind of counterintuitive. I found this myself, and that like, especially for contractors, I'll just tell you about like a little problem dealing with it. So I have like many things to do, right? Actually, the thing I know how to do best is like design the circuit, right? But I've decided to contract out the design of the circuit. And the reason why is that like I know exactly what needs to be done. I know exactly how to do it. I know exactly what a good result looks like, and I can tell if like someone would be able to do it. And so even though I could do that, that actually is the easiest thing to contract out. Yeah, that's like one thing.
I guess so. So since you're sort of in startup founder mode, right, with this kind of thing, we actually do have a lot of founders, usually younger founders, that listen to these episodes. So give us some more guidance and experiences on your end, because I know, like for instance, so we're working with Augmentation Lab on their summer residency in Cambridge. I'm sure you've heard of Augmentation Lab before, right?
Oh,
and
I know Andy.
yeah. Oh yeah, they're awesome. Yeah, they're.
Yeah, I say see how. Yeah, I know. I think all the guys I know are leaving now. Alan's leaving. Lucas is leaving. Yeah.
But yeah, so we have a lot of people in sort of the startup world. Younger founders, especially interested in unconventional computing, biocomputing, human augmentation, brain augmentation, all that kind of stuff. So I'm like, what type of advice would you have for those younger founders going into the augmentation space? Because I think one real practical big issue is just regulation on this stuff, right?
Yeah. You gotta know how to make stuff. Like you just gotta know how to make stuff. And honestly, like you should probably learn how to make normal boring stuff first. That's my opinion.
This is the crawling before running thing, right? And where did for Paul? So when does this all start for Paul? Where did sort of the building engineering bug first bite you?
Yeah. Oh, by the way, one thing, Morgan mentioned this biohybrid electric platform. That's exactly what we were just talking about a bit. And that, like, okay, in this one, they actually grow the neurons on like electronics, and then they implant neurons into the brain. Okay, and that actually relates to what Yo-Yo was over here last week, like yesterday doing. So like if we go to that's basically the application something like this. Because for many years, since about like 1995, that's when like I think they first started doing this. Like they can basically create a circuit board. This is really just like a bunch of electrodes, a bunch of pads, a wire. It looks just like a circuit board, but instead of like putting a chip there, you grow neurons in a petri dish. The challenge is that like if you try to grow neurons on like regular circuit board material, they don't grow. I've never grown neurons myself, but I hear that they're pretty, they have bad temper and they don't seem to want to do very much. So actually, yeah, the trick with this is I think a lot of literature, they use titanium nitride. Titanium nitride is what they use in pacemakers. I actually have some in the fridge right here. I'll actually bring it in the fridge. This is in the fridge. I don't know, it's like titanium nitride nanoparticles. One problem with titanium nitride is that it's not, so it's actually conductive ceramic, so it's like inert to the body. Another problem with it is that it's opaque. So actually, I just read a paper recently that was able to make titanium nitride that was transparent. Because like if you want to do like microscopy, like if it's easier to see. But actually, back to the question about startup stuff. How do you get started? So actually, yeah, I'll just show you. Okay, yeah, this is some of the stuff I did as a kid. The very first thing I did as a kid, I was like in 8th grade and I made this. No, I was in 6th grade. So when I was in 6th grade, I saw a video of one of these things working. Okay, what is this? Imagine like this playing music, but the music is like coming from the plasma. Like in the same way that like, for example, actually this is an arc rectifier for like old movie theaters. Like this gives a very bright carbon arc lamp. That's what that is. Anyway, all right. So basically, like thunder and lightning happens, right? So there seems to be proof that like electricity and high voltage electricity can cause sound. So what if you just like modulated that electricity in like a sophisticated manner? You could turn that sound to the music. That's the idea of a plasma speaker. You use the plasma like lightning and make it play music because you modulate the electricity like you would like modulate the electricity go into like a speaker cone. And actually, from like a technical perspective, this is a speaker. It really is a speaker because what is a speaker? If you look at a picture of a speaker is electromagnet moving a diaphragm that causes air pressure changes or sound waves. So in this case, the plasma is the diaphragm. It's actually causing the air to expand and contract, and that's what's causing the music. So when I was in 6th grade, I like went to the librarian whose like husband I think was electronics enthusiast, and I was like, I need to learn how to read schematics. And I learned how to read schematics in 6th grade. And then by about 8th grade, I was able to make something like this. And yeah, it works. But it goes even farther back than that. Because when I was a little kid, I took apart everything. I like took apart alarm clocks when I was like 5 years old. I remember one time I like took a bunch of stuff and like wired it all together. And like I kind of stood back. I was like 5, 6 years old. And like I waited for something to happen. Nothing happened. And in that moment, I realized that like design is about intent. You can't just put stuff together and like something happens. You have to actually like have a sort of a plan and intend. And
totally. Yeah.
That's how I got started. I tried to and then I was just like I love cool stuff. I'm sorry I haven't spoken too much on the sort of like where the future holds for this. The problem is like, you know, the human brain is limited. A lot of people working on that, right? But it's limited so far as of this moment. And you know, when you like kind of zero in on like, okay, how am I gonna make this thing? How am I gonna sell it? Like, what's practical use case? It's really hard to also think about sort of like the big picture, like what's gonna look like.
Totally. Yeah.
I think that's why there's a need for both. So I really appreciate that sort of discussion. Other things I did was yeah, I was into old radios. I like fixed old radios as a kid. And yeah, I took this whole thing apart when I was like 13 years old and like rewired it together. If you're gonna make bioelectronics, be good with your hands, because if you want to make software or you want to make like, I don't know, like some sort of like AI wearable that has a camera, you can just order on JLC PCB. If you want to do bioelectronics, you gotta like actually go in the lab and like make stuff. It's really hard to make stuff, actually. It's really hard to make stuff. It's really hard, and it takes a lot of practice. One thing that is interesting is that like I would encourage taking stuff apart. I would encourage taking stuff apart, and I would encourage like treating stuff as though there is a purpose for everything. So for example, like if you talk to like a technician versus an engineer, because when I was a kid, I was in the old radios, and I always talked to the technicians on like the, okay, there's something called here. It's called the Antique Radio Forum. I was on this all the time as a kid, where like I collected antique radios.
Yeah, I've seen this before. I know this website. Yeah, yeah.
I've been posting. I was posting on this like when I was like 12 years old, pretending to be like 15 or something. Funny
Was
enough,
this like 2014, 2013, something like that?
that's correct. Yeah,
Yeah. Well, what was your username on there?
I think it was for a while it was just my name, Paul Hahn, but I think I changed it to I don't recall. But why? Were you on there? Did we happen to?
No, I used to scroll around on a lot of these different forums. I'm just trying to remember if there was any particular thread that I'd read that rang a bell. Are they still active these days?
I think they're still talking about how incandescent light bulbs are great. You know, that thread was like 100.
Yeah.
That thread was like 100 pages long. They really liked the iron light bulbs.
Yeah.
Another thing I was on was like I was on the cassette tape forum where I learned how to repair cassette decks. It's actually really hard. I was at tape heads net. I'll just show you something.
It's interesting how the interface is so like antiquated. I actually kind of like that it stayed the same because it takes you back.
I have this like, okay, when I talk about like, philosophy, okay, so I do think that like, you know, like different forms of communication have affect like message, blah blah, everyone knows it's
Yeah.
now. But so like with the old forums, like you could do really sophisticated engineering, like with like Tesla coils and etc. Like on the old forums, like the PHP forums, like you could do really sophisticated technology discussion. It's not really possible anymore with like Twitter or like Facebook, whatever. I want to show you some pictures of like what. Oh yeah, this is me. This is me. This is me restoring a cassette deck when I was like a kid, and you see me like taking apart all these motors, and like I would like take the whole thing apart, like clean it, like grease it, pull it back together. Yeah, if you want to do bioelectronics, you gotta kind of know how to make stuff, because like the reason why I've been talking about all these boring like material science things the whole time is that like you kind of have to like invent how this stuff is made a lot of the time.
Oh yeah. Yeah,
And, like,
someone did all of this. This didn't just pop out of nowhere. Someone put in a damn like large amount of time and hard work to make even the screens we're communicating on right now. I mean that's extremely important. I think there is this thing where sometimes I've met other builders that will sort of, like what you were saying earlier, like they'll expect the thing to just work, but I'm like, no, you have to actually make the thing work. Like you have to put your intention, like you were saying, into that, right? And that's an art and a whole nother skill in and of itself in a lot of ways. And I think part of it is I think it's not just it's building things, but then also the way that you're sourcing things, because even though it's boring to a lot of people, like where are you going to get the parts from? How are you going to be able to afford all of that? And if you want to scale it up and build it, these are all very, very real problems that, they're kind of more boring comparatively to all the sort of dreamy, lofty stuff, which again, I love that, but I also think it's extremely important to have that groundedness about how do you actually take this very conceptual thing, even if you've made a CAD model of it, great. How do you turn that real? Right? Even if you have the thing 3D printed, you have it CNC machined, whatever, like there's a lot of different fine-tuning things, especially if you're working with smaller devices because of tolerances. That's a pain.
Try to 3D print a screw in a thread and get the screw to fit in the thread. It will take you like probably 2 weeks if you're good. It will take if you haven't. It will take you like 2 weeks to actually get this to work really well. Actually, it's interesting in that like you have to think. Engineering is about constraints and tolerances. The origin of all engineering is in precision. Like you ever think about like how do they create a ruler? It's like how do you do that? Like in the old days, you had the weights.
A ruler or a clock. Yeah.
I use the Aurem Labs 4.4, which is like like a resin printer. It's like it's like fairly affordable. It's like $4,000. And like this has like a 25 micron resolution. If you try to get like some cheaper printer like the Elgu. So the interesting thing is that if you look at the specs for the Form 4 versus the Elgu, which is like $500, and the Form 4, which is $4,000, the specs for the Elgu are actually better. But in real life, the Form 4 beats it hands down. The reason why is that like, okay, it tells you it has a 16K screen. But if you actually look at how if you actually look at how a resin printer works, basically what they do is like they have a mechanical arm that will like kind of like move this plate down. They will flash the resin, move it up, move it down. So to build anything reliable, you actually have to have a moving arm that moves up and down thousands of times for a single print, and it's consistent across prints.
Right, and it's got to be able to. I mean, a lot of things. When I've worked with 3D printers in the past, is that sometimes they can be a little delicate at times, and if you're not careful with it, even just having some of those little things off can screw up the print. Even temperature, at least with normal 3D printers that aren't necessarily resin, is that you'll have that issue with temperature and humidity and all that as well. And it's like those are all very real engineering problems.
Practical advice for people interested in bioelectronics. Okay, so this is unconventional advice, but first of all, save up the money to buy good tools. So like you want to spend like $200 on a soldering iron. Don't buy Weller, buy Heiko. Buy a Heiko soldering iron. Don't buy the FX888D. Buy a different one because you want integrated ceramic heater with your tip. You don't want a separate heater. Sorry, you're not gonna remember that, but just buy an expensive soldering iron. That's my tip, and don't buy a Weller. Number two, learn how to read schematics, and learn how to use KiCad. That is important advice. When I first did it, I learned on like EagleCAD, which was like the tutorials. Second of all, I think if you want to do bioelectronics, you can't be afraid of like touching stuff. Like if you think that like if you get rubbing alcohol on you that you're gonna get cancer, like I just don't think that this is the field for you. Because like there's just a lot of chemicals, there's a lot of weird smells. Like lead solder is better. Like I trust me. Like I just don't think I don't think a successful engineer would like would willingly choose lead-free solder versus lead solder. That's just my like random opinion. It's so much better. And take apart a lot of stuff. So what are some things to take apart? You want to take apart like so buy one of these and like take it apart and yeah, buy one of these, just find one on Craigslist, buy it and take it apart and like figure out what everything inside there does. You won't understand the theory of like how the circuit diagrams work, but like you will at least understand like what different components do. For example, like I can tell you why this looks the way it looks like. You should be able to have a basic understanding of like why this looks the way it looks like. And another thing is another thing. So with software, I feel like it is much easier to build something is to figure out how it works. And so like oftentimes in software, the advice is to build something. In hardware, I think this is a bad idea. This is a bad idea because it's really hard to build hardware, and like your imagination will only take you so far. It's much more tractable to figure out how a piece of hardware works than it is to try to build a piece of hardware. So before you try to design electronics, try taking electronics apart. I really want to emphasize that.
You really do learn a lot by taking things apart, because it's not just taking things apart, but it's how you take things apart, because certain things, if you take it apart, it's basically destructive. I think part of learning how to reverse engineer and take things apart is to know how to take the thing apart while not breaking or damaging anything. Like, there's certain remotes or whatever you could take apart, especially if they have their the plastic ones with the injection molding, whatever, where they snap on in these very tight ways. Like, you have to be very careful. Oh, I remember it was the what was it, the iBook G4s? I think it was those ones. So I used to take those apart a bunch, right? I used to get a bunch and take a bunch of them. And it was a pain to take the plastic casing on the clasp inside off. Like, because you have to use, some kind of flathead thing or whatever, but you don't want to dent or damage the plastic. How do you do it? Well, maybe you can take a little heat gun, gently heat it up, but you don't want to do that because there's electronics inside. There's all this kind of stuff. And I think the art of learning how to properly take things apart is also very important as an engineer, physically, without breaking and destroying the whole thing. Does that make sense?
Yeah, that's perfect. That's I like how you mentioned the tabs on the G4. It's really annoying. One thing I like about the older stuff is like much easier to understand and take apart.
Yeah.
I always break the tabs. I think you have to be superhuman to not
Yeah.
break the tabs. All right, I guess I think this is like a good. Unless anyone has any questions, like I'm free to kind of like close
If
off.
anybody has some lasting questions, comments, ideas, real quick.
That comments from experience too. I bought the Vision Pro trying to figure out how to hack it. I gave up.
Do they like? Oh yeah, if you want, it's annoying because okay, so like you basically need that. You need a microscope. You need like a stereo microscope that costs like $1,000. You need like a desoldering iron. You need like these like I have these like Weller. I have like so I use like JBC soldering irons that are like it's like probably $1,000 to get the whole kit. Yeah, I don't know. I feel kind of lucky because like I was right at the cusp of like I used to go to Goodwill a lot. I was right at the cusp where like the Goodwill was like full of like old stuff and I could just buy it really cheaply and take it apart and figure out how it worked. People like a little younger than me didn't have that experience and it's just gonna get worse, just like Eli says. Eli said that like as tech gets more advanced, that device is gonna be harder and harder to follow. More hardware will get closer to Vision Pro in terms of being able to reverse engineer. So yeah, I don't know. I don't know. I guess for me it's a little advantageous, but yeah, I think it's gonna be harder and harder to like kind of do this kind of stuff unless you invent new games, which is why you can start with bioelectronics. These bioelectronics that no one's figured out how to do it yet, so you can kind of just invent stuff along the way and it'll be easier. But it's expensive. I would save up some money. Yeah.
Awesome. All right. Well, this was a really fun time. This was a little different than this is definitely more engineering focused than some of the more sciencey, philosophical stuff that we do. But I think it's very needed because I think something that happens a lot of times in those circles is that we are not as grounded as we could be about things. And I think talking to engineers that actually literally physically build something is a very incredible and sobering thing to do. So thank you, Paul. I really mean that. And I guess the last thing on your end is, you know, of course, where can people find you, but then also who are you looking for to connect with or work with for Aurem Labs? Because I think this is a very cool project that you're working on. I think lots of cool stuff is going to come out of it.
You know, it's funny you caught me at like the time at life I'm in right now. I think like 4 or 5 years ago, I would be much more philosophical in talking about those things. But yeah, just really in the startup mode right now. My name is Paul Hahn. The company is Aurem Labs. We make biofeedback electronic wearables. Our initial product is called Aurevelum. They are EMG 10's electronic notes. You can reach me on Twitter, X, Signal, email, passenger pigeon. And what we are looking for, we're raising right now. We're raising $400,000, and I'm looking for basically scientists, engineers, and people skilled in materials engineering. That's all. And I'm in San Francisco. And yeah, I'm a great boss. Thanks.
Awesome. Real quick, I wanted to ask you about why you said 5 years ago the philosophical thing would have been more of your kind of thing. Why the transition?
Well, you know, it's funny. I actually majored in political science and electrical engineering. And actually in school, I spent most of my time studying political science and like actually read all of the Beat Generation. I read like Burroughs. I read On the Road. I've read like classical philosophy and stuff like that. You know, it's funny. Founding fathers have this little tidbit where like they all talked about Aristotle, but like never actually read Aristotle. I read a little Aristotle. No, that's just how I am. But you know, like I don't like it when people my age say they're old. I'm not too old, but I'm not too young either. I'm 26 years old. What's nice about this age is that like I feel recently I started to get to the age where I could start doing things. So I'm doing things, and that's why I founded a company. Thanks, everyone.
Perfect. All right, I love it. Thank you, everyone. You take care. We'll have this up soon. What did y'all think about this one? This one was actually the last one, and this one were also sort of a change of pace for all the Polymath Salon stuff, because Paul is an engineer, Paul is an engineer, and then Peter earlier was an AI researcher trying to build AGI, And we had an interesting perspective with, say, Dr. William Hahn, and Peter Voss, who are sort of slightly different schools and generations of thought on AGI. And then we have Paul, who's an engineer building electronic skin. So what do you guys think about this one today?
This one
quite
has,
fun to listen to.
Yeah, this one for me has more practical application.
Right.
And I do think there's some crossover into the sciencey and philosophical side of this, because very soon this hardware will be interacting with thought.
Yeah.
Right? Right now, we're just trying to get basic electrical signals up and back that stimulate, response from mechanical devices, but
Right.
that's bordering on thought. Activating a mechanism, so or sensory input activating thought, right?
Yeah.
So
And I, for me, in a lot of ways, being a good sort of being a good builder is sort of applied philosophy in a lot of ways, right? When I think about, especially in the way that we've kind of differentiated between technology and biology, I really do feel that in the future, a lot of things, I think technology will start to look like biology. I don't think it'll necessarily become biology. I don't think we have to necessarily use the same materials and frameworks as biology, but I think because it's the types of goals that you're solving, right? So I've talked a lot in previous salons about, how these fields that we call chemistry, physics, mathematics, philosophy, whatever, emerge from certain problems that we're trying to solve. And solving problems is very much sort of an engineering thing to do. You're trying to solve a problem. You're trying to build something, change something to solve this issue, right? And I think that because of the problems that we're trying to solve right now, when it comes to things like AI, intelligence, at least as far as we know, was always biological, in a sense, at least in our scope of things, right? And so, of course, it would seem that if we're trying to solve the problem of intelligence, it's going to start to look a little bit and trend towards something that we would call biological intelligence. Doesn't mean it has to end up in the same way. I don't think it necessarily has to, but it is interesting because, when I think about, if you were to recreate bones and skin or analogs of them for some kind of robotic system, right? Even if it doesn't look like a human, it could look like anything, right? There is sort of this principle about you have this skeletal structure that's giving rigidity and structure to the whole thing, and then the interface on the outside that lets it more quickly adapt to different things and move around and all that. And it's sort of like, how many different ways would you make a joint that can move around like this? Right? Especially within material constraints.
Think about that. When AI is at the point where it can design its own body.
Yeah.
We talk about sentience, and maybe there's a corpus required to have sentience in the way that we think of it, at least, we don't know how to define consciousness, but let's say that a body is of some sort, a physical body is required. When AI can design its own body using what we're thinking of now and expanding upon that, right? Because we're creating building blocks now to build much more sophisticated models 5-10 years out or less, then what does that if it's an AGI, what does it design for its own body? Right?
Yeah.
I just saw a video of, I don't know if you've seen this, an electric horse, a robotic horse that's electric. Oh my God. It's amazing. I don't know who the builder is, but and people were riding these electric horses, and it wasn't a fake video. They were clearly
that's some Westworld stuff right there.
Oh my God. Yeah.
Yeah.
But think about it. So, AI design, at least augmented by AI, to design a physical body for an AI mind. What would that look like?
I guess what you're getting at is what happens when a system has direct access and control over its source code, in a sense, right? Like, it's sort of like what Dr. Allen was saying earlier. Like, we don't necessarily have, I don't know exactly what's happening in my liver or kidney right now, I can't necessarily control it, right? This is actually something I'm very interested in, about how do you gain like master control over the body, right? You know, how can you sort of be aware of you know, of more so of your heart, your liver, spleen, all these different things, but not also just be aware of it, but also be able to control it and use it for various things, because you know,
We have
I
some
think
control.
we have some. Now there are certain, you know, mystics, intensive meditators, and things throughout history, and a lot of that literature that have talked about these sort of ideas of a master control of the body, like they're able to be more aware of different things happening in their body, different organs, gain some control over them. I don't doubt that that's possible. It's just, it's also an engineering problem of how you do it, right? And for me, you know, like I think a lot about you know, the sort of thing I was talking about earlier about like the material properties of agency, right? And how do you build something that actually can heal itself and grow and adapt, right? Because it would be very, it's, you know, I think Dugan was also there for this salon, but I was talking about like, you know, if you have something like a GPU, right, or a circuit board or PCB, right, like we have no problem saying that the sort of software aspect of that can sort of, it has access to its source code to a degree, it can change and update and adapt. But what about, can the hardware adapt? Yeah, there's physical things happening in the hardware when you're running the computer, sure, but what can you actually literally physically get it to change the way it's orchestrating things and the way that the particles are physically organized, move around all the different, you know, like when your brain is exposed to certain kind of stimuli and reorganize, this thing that we call plasticity, right? What does the plasticity look like about, you know, physical circuitry and circuit boards and GPUs? Right, a GPU where you can train the GPU to get better every time. You take the properties of AI, you know, that you'd say sort of exists in the land of software, and then bring that into hardware, right? Learning materials, I think, is extremely.
We're getting into biological computing now, though.
Yeah.
Right.
Yeah. But the question is
self-healing, self-replicating.
Right. But the question is do you have to? How much of this can you get away with without using materials that are already found in biology, right? Is there some other way that you just for sake of argument that you could make things that behave very similar to biology but use a very different set of materials? Now I do feel that you're probably going to end up trending towards the same kind of distribution of a harder skeletal like system and a softer shell exterior, all these different things. I think you're going to have various things where whatever needs to be most adaptable is going to be the softer thing, and whatever needs to be the most structural is going to be harder, right? Because even if you look throughout biology, like everything that's like a skeletal system or a wall-like structure that's giving it, you know, literally a boundary is technically harder, even if by a very small amount, than whatever else, right? You know, even a cell wall, right? Even that's got to have a certain material property where it keeps the thing clumped together instead of going apart elsewhere, right?
Well, that's an interesting thought. What if you have a central nervous system that can operate autonomously with or without structure? It would have the best of both worlds.
Yeah.
Right? And why wouldn't it design itself that way? Right? Yeah. Because the physical structure itself is self-limiting. But it also creates capability that's impossible if you only exist in the ether.
Yeah.
So why not have both?
Why not have both? Yeah. Yeah.
And we kind of do. You can meditate or put yourself in an altered state where you're somewhat separate from your physical being.
Yeah.
However, your physical being is necessary for that ethereal self to operate. I mean, that gets into a whole metaphysical question, but we don't know what happens when when the physical, certainly whatever consciousness we can experience of others goes away when their body goes away, when their physical corpus ceases to.
But this is also the thing about, you know, people that talk about sort of transplanting their sense of self, their consciousness, whatever, into some other agent, whether that's literally into another biological body or, you know, an AI robot thing, whatever it is you have to ask yourself, well, what is it that you're transferring over? I don't think just reading and writing to another brain is going to be, I don't know if it's going to be that simple. Right. And you have to think about the way that, just memories and information is stored in general in biology versus current computational system. And I am a fan of finding a way that you can get the best of both worlds. And I feel like, one of the things that I don't think is looked at enough is this thing called savant syndrome, right? You have things, people that have sort of, to at least some extent, the, inborn capabilities of, a decent computer when it comes to calculating and visualizing things, right? And, I don't know too many people that are looking at this phenomenon, but, usually savants, let's say they're born, on the spectrum, and if they take an IQ, an IQ test or something, they might flunk it. They might not do a very good job on it, but then they can also like visualize crazy shit, imagine crazy shit in extreme precision and detail, make very complicated musical pieces, visual artistic pieces, incredible memories, mathematical, exactly.
Yeah.
Right. And what's the crazier part? It's the freaking the acquired savants, the people that get knocked in the head, and then later on they wake up with these insane capabilities. What is that? Is that not the craziest thing you have ever heard? You can knock your head and you wake up a genius? Is that not
Hormesis.
It is hormesis. I have a lot I can say about this for hours, right? But why is that possible? Why is that? That's what I'm saying. Is I think there's something.
I think happens.
Yeah.
I think that the conscious mind, what we call us, just gets like better tethered together with the unconscious mind, and unconscious in quotation marks, because I think it's actually conscious as well, and is able to tap into some of its computational resources.
Well, this is actually something I believe someone had looked at this for savant syndrome, at least for drawing ability, probably years back now, but it was on accessing sort of the lower level so-called unconscious sensory information, memory processing, whatever. And I think they did use some kind of electrical stimulation helmet thing for it, right? But long story short, they electrically modify through one of those helmet things or whatever. They electrically modify the brain in such a way where they were more able to focus on the sort of lower level processing of the brain when trying to draw something, right? Now, and they could draw it better. Now, here's the interesting thing is that you can do this without any other device. If you want to draw better, like you're trying to draw a face, all you have to do is take your reference photo, flip it upside down so it's unrecognizable, and you're going to probably draw it much more accurately. This is something a lot of artists will try to do. It's the saying about draw what you see, not what you think, right? And if you want to get even more wilder with it, is you can, sometimes people will literally, you can take, an image, the reference image, you can cut it up into little squares, and then you just focus on drawing the squares in, and that's it, so that there's no other context to it. And if you do that, and then you draw the whole thing, that also ends up looking better.
Well, there you get features, right? Features.
There's something about the way that you're thinking about this stuff. There's something about the way that you're thinking about this stuff that is interfering with sort of the so-called raw information. And it's a compression thing, right? It's very much
Also, the Comic Sans one was more like for people with dyslexia, and I don't exactly know where the optimizations and deficits, exist. And obviously, it's not a universal thing. But yeah, compression definitely seems like the less compressible, maybe the more you are forced to have normal type of attention to it. I don't even, there's too much to understand.
Yeah. Well, it also thinks about cognition as something that does function off of some kind of compression. And I might be using compression in a different words than say some other computer scientists might be saying it. But, what are you doing when you're compressing things? You're trying to, it's like you're saying you're trying to get more out of less. Like you're compressing, a lot of stuff into something small and still getting some usefulness out of it, which is also what we'd call a generalization. All right, we also spoke about this in the one with Dr. Han and Peter, right? About generalization. Is that when I'm learning a concept when I'm learning something and I'm turning it into a concept, into a generalization, right? Something that I can then repurpose later on, you know, increasing its sort of general purpose, is that you reach a certain level of generality where it starts to be like, this thing is happening, this thing will happen. Like, okay, this thing is doing something and this thing will happen, but it could be literally anything. I'll say something is going to happen in 1 minute. Well, yeah, something is going to happen in 1 minute, but you don't know what that is. It could be literally anything, right? And so there is this thing about intelligence and information processing, whatever you want to say, that is finding, almost like the hormesis thing, Michael, there's the sweet spot in that distribution curve of what's the right amount of the optimal amount of generality and specificity, because the generality also loses its usefulness if there's not specificity with it. Which again, you know, when you try to think, when I do a lot of just experiments in my head of trying to think more generally about things, you start to reach a point where it's like, this thing is happening, this thing is transforming. And it's like, okay, good. But that could be a million different things. And so I think there is this sort of capacity, this sweet spot where you have maximum generality, but then also that maximum specificity. And they're not necessarily against each other, generality and specificity. You sort of have to have both.
Well, we operate in a very high ambiguity environment, right? With a tremendous amount of data to sort through. So a capability that's really essential is ruling out. So we throw away a tremendous amount of data just to be able to function. And
Yeah,
really neat exercise. So I'm sure I've shared, you know, I do Tai Chi and Qigong, and if I close my eyes when I'm doing some of it, it's very difficult to do because you have to maintain your balance. But
yeah,
through a lot of it now, I will close my eyes and the experience is completely different because I shut out all that visual input.
right.
Right. And it allows me to center in a different way.
Yeah,
But this is something that we will see evolve as
totally.
as we develop these whatever we want to call them, consciousnesses or
Yeah.
AI models that
Minds,
have
yeah.
access to unlimited, you know, infinite amounts of information, depending on the purpose that they're operating on, and they will have to be able to rule out and filter out a lot in order to function,
Well said.
right?
Perfect. Perfect, Ender. All right. Thank you, everyone. This was a lot of fun, as always.